So thank you for having me. My name is Rodriguez-Pardo. I'm going to present SeamlessGAN, self-supervised synthesis of tileable texture maps. This was published as a journal paper in TVCG in January of this year, and it's joint work with my advisor, Elena Garces. So just to give you an outline of the talk, we're going first to see a motivation on why we need texture synthesis. We're going to see some related work on this topic. Then we're going to dive into SeamlessGAN, how we train it, how we sample from it. We're going to see some evaluations and results that we obtain from the model, and just feature work and conclusions. So in terms of motivation, so in order to create realistic 3D environments, we need digital materials. So for example, if we wanted to create these scenes in a virtual setting, we will need accurate representations of the material that appear on the images. So you will need representations for fabrics, for leather, wood, metal, etc. This is usually done using textures in virtual environments. Textures are a specific type of image which contain repetitions on a pattern. And textures are like everywhere in the real world. So for example, they are in our buildings, in our cities. They are also in our garments, in what we wear, in our clothes. They also appear in our food, and they also appear in nature. Also, when we write, and we create this kind of texture patterns in images. So textures are everywhere, and we need a way of digitally handling them. So we need algorithms that can generate textures automatically, so we can use them in virtual and digital settings. This is useful in many cases, including software for design purposes, for video games and movies, and also for virtual reality and augmented reality applications. Textures are really important. One important thing to consider when using textures in these kind of settings is that you typically need multiple maps to represent the material. This is known as spatially varying BRDF or texture stacks, which is just a collection of maps, each of which is an image, and each map represents a different property of the material. So for example, the normal map represents the microgeometry of the material, the diffuse or albedo map represents the color, the specular map represent the specularity of the material. Having multiple maps allows you to provide an extra level of realism to your material. So just to give an example, this is what happens when you only use a base color map or an albedo map as your material representation. It looks okay, but if you use more maps, including the normal map or the specular map, the material looks way better. It has this extra level of detail that you really need for realistic environments. Another important factor to consider for this is using tileable textures. So what happens when you use just a raw image that you can capture with your smartphone, for example, like this image of a fabric, is that it represents a portion of the material. So if you want to cover a larger portion, a larger object with this material, what you will do is just repeat it horizontally and vertically, which in this case creates this kind of repeating artifact that doesn't look that great, and you can tell really easily that it's being repeated. However, if you get this image and you make it what we call tileable, this happens that when you repeat it, you cannot really see that it's being repeated. So it allows you to create large objects with this material with only a really small portion of the texture. Turning an image into a tileable texture is a really challenging problem, and there's plenty of solutions that work sometimes, but not always. So just to give you another example using renders, this is what happens when you use the image I showed before without the texture maps and without making it tileable. You can really see that it's being repeated multiple times, and this doesn't look that realistic as a garment. If you turn it into a tileable texture and you add these extra maps, including normal map or the specular map, you get this other image which is more much more compelling, has no repeating artifacts, and looks generally better. So the question now is how can we turn a texture into a tileable texture using algorithms? So to understand that, we need to understand what has been done before in terms of texture synthesis and tileable texture synthesis. I'm going to talk about some papers briefly. This is by no means an exhaustive list. If you want to know more about the topic, read the paper or read other papers on the subject, because there are plenty of texture synthesis papers. So just to understand what texture synthesis is, it's just a special type of image synthesis in which the image you're trying to synthesize has some kind of repetitions on them. So just to give you an example, this is an image of a texture. You run it through a synthesis algorithm and you get another image. This is obtained by SeamlessGAN, which represents the texture of the input image, but it's not a copy of it. So texture synthesis is this kind of special synthesis problem in which there are repetitions on the image. Textures in the real world lie on this kind of spectrum of regularity. So man-made textures are typically more regular, and natural textures are more stochastic. So what happens is that a synthesis algorithm that works really well for regular patterns doesn't really work that well for stochastic patterns, so, and vice versa. So generality on this spectrum is really hard to achieve. There are two main categories of texture synthesis problems, algorithms, sorry, that you can divide the literature into. So non-parametric texture synthesis work by getting patches of the input image and creating a new image by getting those patches and modifying them using different approaches, including image quilting, graph cuts, optimization, etc. These are typically faster, but the results they obtain are not that great. On the other side, we have parametric texture synthesis, which is a kind of group of algorithms that how they work is they learn statistics from the input image, and they create new images that have the same statistics as those you have learned. So for those, you have more recent approaches, including gradient descent, optimization using CNNs as your image descriptors, or you have GANs mostly. So these algorithms typically rely on learning and are more flexible and are more general and obtain better results, but they're way slower than non-parametric synthesis algorithms. So in this family, you have GANs, which are also state-of-the-art for image synthesis for faces and people and landscapes, for example, and they are also state-of-the-art for texture synthesis. So just to give you an example of how a non-parametric synthesis algorithm works, this is a seminal paper. It's over 20 years now. So you just get some crops of the texture and just create a new one by repeating those crops and blending them together with different methods. In terms of parametric texture synthesis, kind of a seminar work too is this paper by Gatis et al., which are the people that did the original style transfer algorithm. So they use pre-trained VGG networks as an image descriptor and use optimization to create the new images using those descriptors. This idea was also extended for texture stacks quite recently. So instead of synthesizing only one map, you can synthesize multiple maps using this idea. In terms of GANs for this problem, there's this paper that uses an idea of adversarial expansion. I will explain it later. These kind of methods take one image as input, and they train a GAN for that image and generate results that are great, essentially. They are state-of-the-art for multiple types of textures. However, they take several hours to train for each new image. This idea of GANs for textures can be also trained using a data set of images, in this case, satellite images. This paper, TileGAN, is relevant for SeamlessGAN because it provides some idea of manipulating latent spaces in generators to create new images. We borrow some of these ideas to create seamless textures. So in terms of tileable texture synthesis, most of the published work on this topic is non-parametric. So they inherit the limitations of non-parametric synthesis. So this paper uses patch match as a way of synthesizing tileable textures with a toroidal constraint, I think. This other paper uses graph cuts to blend an image with itself, so it becomes tileable. This is a different paper which works in real time in GPU, which works really well for stochastic textures just by tiling and blending using histogram blending. This is a paper actually from me and other authors. What we did is just get an image of a really regular texture, find the optimal repeating pattern and blend it with itself using Gaussian blending. Works really well for regular patterns, but doesn't work at all for stochastic patterns. In terms of parametric tileable texture synthesis, there's this GAN which enforces tileability by putting a periodicity constraint on the generator design. Works really well, but it's also slow and has the limitations of parametric synthesis. This is a very different paper which uses neural serial automata as an image descriptor. What they achieve is really cool results, but takes a long time to train, and the resolution of the images is really low. They can only produce low resolution images, and they also are limited in the semantic understanding of the textures they generate. So this is kind of where SeamlessGAN comes in. We want to achieve three things with SeamlessGAN. The first is to achieve tileable textures. This is our main goal, hence the name SeamlessGAN. We also want to achieve multi-map synthesis, so being able to handle multiple maps at the same time. And we also want to achieve the quality that you can only achieve using GANs. So this is where SeamlessGAN comes in. SeamlessGAN has two main parts that I need to explain. First is the training, how we train the generative model, and then how we sample from it. So in terms of training, we simply use this idea of adversarial expansion. We make it work with multiple maps at the same time, and we make it faster. So instead of taking 5 hours to train, it takes 40 minutes. It's a long time, but it's faster than state-of-the-art methods. And in terms of sampling, this is where kind of the main idea comes in. So we do not train SeamlessGAN to generate tileable textures. We sample in a way that allows us to generate tileable textures. So we have two ideas on this. One is manipulating latency spaces in the generator, and the other one is using the discriminator as a qualitative function during the sampling procedure. So in terms of how we train the GAN, there's this adversarial expansion idea, which we borrow from the paper I mentioned before. So this is a test stack. On the left, we see a base color map, an albedo map, and on the right, a normal map. For each element in the batch, in each batch in the training, what we do is randomly crop a portion of the material. This becomes a target, our target, what we want to generate. So to generate this, what we do is crop another portion of this target, which becomes our input to the generator. So we feed this input to the generator, and it makes its prediction. In contrast to other types of GANs, which receive a random vector as input, we use actual parts of the material. So this is easier to train. So how we compare the target with the prediction is by a combination of loss functions. So we have pixel-wise norms, which just typical, comparing each pixel with each other. We also have a pre-trained VGG network that allows us to provide a style kind of loss based on style transfer. And the main component of our training procedure is the discriminator, which becomes our adversarial loss. So as in standard practice for GANs, we first, for each element in the batch, we first train the discriminator to distinguish between real and fake images, and then we train the generator to provide more realistic images. SeamlessGAN has a fully convolutional generator, which basically receives as input a crop of the material, passes it through an encoder. This encoder reduces the spatial dimensions of their input by half. This goes through a set of residual blocks, which are just convolutional blocks with residual connections on them. And we have one decoder for each map in the texture stack. So in this case, we have one for the albedo and one for the normal map. And this generates an output image which doubles the resolution of the input. That is what we call adversarial expansion. And this is what makes our method self-supervised, because there's the input and the target part of the same image. To improve the quality of the results with respect to previous work, we use instance normalization, which allows us to obtain better results because we train it with a better convergence properties, and this allows us to train it for half the iterations. The discriminator is a patch scan discriminator, which instead of providing a prediction for the entire image, it provides predictions for patches of the image. So this is common usage in different GAN papers, including many image-to-image translation papers, VQ GAN. It's typical to use patch GAN because it provides a fast yet really a powerful way of distinguishing between high quality and low quality patches in the image. We also use the discriminator as a test time quality metric, which is what I will explain now. So in terms of implementation details, we train it for each new texture. We train a SeamlessGAN from scratch for 50,000 iterations. For this takes around 40 minutes on a 1080 Ti GPU. We use mixed precision training and automatic gradient scaling. This allows for faster training as well. And we use PyTorch for everything. So sampling from SeamlessGAN is quite tricky to explain. I hope I will try my best to do it. This is kind of the main idea of SeamlessGAN, of how we generate tileable textures. So if we want to generate a tileable texture from an input image, what we do is crop a portion of the image randomly or manually. It doesn't really matter. We feed it to the encoder. This encoder produces a latent space. So this is half the spatial resolution of the input, but has more channels to it. So what we do now is tile this latent space. So we concatenate it with itself horizontally and vertically. You can do it in the inverse order, it doesn't matter. And we feed this representation to the rest of the generator, which produces texture that has 4 repetitions of itself, but with seamless borders between them. Because the latent space was tiled 4 times, we have 4 repetitions of the texture. So because we have 4 repetitions, we only want one of those. We get the center crop of the texture, and this becomes our seamlessly tileable texture. This is the way we sample from SeamlessGAN. This can be done mostly in real time, so it's really fast. However, what we find is that depending on the crop that you use to feed the generator, we obtain results that may be of high quality or really low quality, and we need to distinguish between them. So to do so, we actually use the discriminator as a quality function. Usually in GANs, what you see is that the discriminator is not really used in test time, which is a waste of resources because you have a really good model that can distinguish between high quality and low quality images. So we exploit that. So for example, for this blue crop, we feed it to the generator and it generates a really high quality image. But with this red crop, it generates this image with artifacts in the middle of it. This is because of the latent space tiling, which sometimes generates artifacts. So what we can do now is feed them to the generator, and the generator will be able to distinguish between high quality and low quality pixels. So as you can see on the black pixels there, the discriminator is able to find that some parts of the image don't look that realistic. And in the image below, you see that the discriminator finds it to be really accurate. So what we can do now is sample multiple times from the input textures by selecting random crops from it and discarding the textures that are wrong, like the one on top, and the textures that are good or of a high quality, like the one on the bottom. We also see that the artifacts are present usually in the middle part of this discriminator output because of the latent space tiling. So we only look for artifacts in that area. So what you would do is sample multiple times, and the ones like the red one, you will discard it, and the one like the blue one, you will approve it. So this is kind of our sampling algorithm. Just to give you another example of this, on the row below, you can see a SeamlessGAN output, and the discriminator provides high quality. It doesn't really find any artifacts. For this one, it finds artifacts in the middle because there are some, and you can see that the discriminator provides a black output in the places where those artifacts are present. So yeah, in terms of evaluation, we're going to see now how each part of SeamlessGAN affects the final output. So how we train it, how we design the network architecture, and how we tile the latent space. So in terms of the loss function, we train our model with each component of the loss function activated or deactivated, just to see what happens. So we see that if we train SeamlessGAN only using the L1 norm, the results are generally doesn't contain any texture. If we use the style loss, it has some texture to it, but it doesn't really work that well either. If we combine the two, that doesn't work either. So the main component, the main driver of the loss function is the discriminator. So if we only use the discriminator, we see that the quality of the results improve significantly, but it contains some artifacts still. So we use the combination of these three loss functions to generate the final training kind of loss function, which provides the semantic understanding of the adversarial loss with the regularization that is provided by the L1 and the style loss. So that's why we use three loss functions. We also evaluate the size of the network. On the columns, you will see the impact of adding more or less layers to the generator, and on the rows, the same, but for the discriminator. So what we see is that using a 4-layer discriminator and a 5-layer generator provides kind of the best results overall in terms of the quality of the results that are produced and in terms of the computational cost of training this GAN. So 4 layers for the discriminator and 5 layers for the generator will take 41 minutes, 40 minutes to train, and it will provide results that are comparable to those of a larger network with less computational cost. We also test how we can generate, how we can design the generator so it generates multiple maps at the same time. So for this particular case, we test 2 different designs of the generator, one that has a single decoder for every map and one that has 1 decoder for each map in the tester stack. So what we see is that using a single decoder for every map produces artifacts that hinders the realism of the output, whereas using 1 decoder for every map produces better looking results and more accurate. Yeah, so separate decoders and the generator provide generally better tester maps. This is on par with what we see in the literature, and there are more results in the paper that you can check if you want to know more about this. We also test where to tile the latent space. So we see that doing this manipulation in early layers of the model works best. So if we tile the first layer, we achieve really high quality results. Going deeper in the network, we obtain worse and worse results the deeper we go. This is because the network can manipulate this latent space fewer times, so it has like less expressive power. So yeah, let's see some results. I'm going to show you some videos first because it's kind of cool, and then we're going to see how SeamlessGAN compares with previous work and where it fails and some limitations of the method. So in terms of just to give you an idea of where SeamlessGAN works, it kind of works in a variety of textures in the spectrum. So you can see that it works really well for really regular patterns like these tile or these basket cases, but also for stochastic patterns like these olive cases. And just a few more examples. These are more stochastic patterns, and SeamlessGAN can handle them perfectly, generating seamless textures. I haven't shown you so many cases of texture stacks. These are a few cases of those. On the left, you can see the input of SeamlessGAN, and on the right, the synthesized outputs. You can see that the generated images are of really high quality in both cases, both fabrics in this case. SeamlessGAN can also produce multiple outputs from the same input. To do so, you only have to crop different parts of the input. So, for example, if you crop this blue crop of the texture, you will get this result. If you crop different parts, you will get different results. So it provides you with the ability of providing some variety on the textures you produce. You can also change the size of the output, the number of pixels to it, by changing the size of the input. So going from a really small crop, you can get this small generated tileable texture, but generating larger crops allows you to generate larger tileable textures. So you can also play with that if you want. Yeah, so in terms of comparison with previous work, we compare with every paper I've talked about before. So histogram blending, graph cuts, repeated pattern detection, periodic spatial GAN, self-organizing textures, and our method. So what we see is that SeamlessGAN produces kind of the best quality results in terms of the amount of detail that is preserved and the amount of semantic understanding of the texture. So in a variety of textures. So these flowers, bananas, corks, and plenty of textures, we obtain the best results in the literature. Some further results, there are plenty of more in the paper if you want to check them. So yeah, and this is what we obtain compared to previous work. We also need numbers to really understand how well we are doing. So we define this quantitative comparison methodology. It's really hard to evaluate with numbers how well a tileable texture synthesis is performing. So we define this methodology in which we take the input texture, we synthesize it using any method. We get the tile, and what we do is tile it essentially. So the output has the same spatial dimensions as the input texture. This allows us to use any kind of perceptual metric to compare the images, the generated and the target image. So what we do now is for every method in our list of methods and a variety of textures of different types, we use a set of metrics, those three metrics, just to understand how well we are doing in terms of numbers. So we use three metrics that are the structural similarity index, which is just statistical similarity between the images, and two deep learning based methods, which are the FID and the LPIPS score. So what we see is that for both non-parametric and parametric algorithms, SeamlessGAN produces the best results, in some cases by large margin. So this is a kind of quantitative way of evaluating methods. SeamlessGAN is not perfect by any means. It sometimes produces not great looking results. So for example, in this case, it fails to generate a compelling base color map because it doesn't know how to synthesize the map. The normal map looks okay, but the base color does not. In other cases, for example, in this case where there is a structure to the texture that is not that frequent, but it's important, what SeamlessGAN typically produces is this kind of output where it essentially ignores the kind of white dots in the original texture. So the infrequent parts of the textures are typically ignored by SeamlessGAN, which is kind of a limitation, even though this result looks okay. So it has extra limitations. These are common with any other algorithm for texture synthesis. So for example, if the texture that was generated is seamless, it may contain repeating artifacts. So even if the texture is seamless, you can see that there are some repetitions, for example, in this case. Also, it needs that the inputs are as frontoplanar as possible. So if there's a confusion between geometry and texture, SeamlessGAN will fail. And also needs textures, it needs images with only one texture on them. So for example, in this image, there are plenty of textures. It will not work because it will not be able to distinguish between textures. So yeah, in summary, we have presented SeamlessGAN. It's a single image generative model capable of generating tileable texture maps. It provides better and faster results than previous work, can handle multiple maps at once, and works with any type of texture in the regularity spectrum. For future work, we would like to explore image pre-processing for improving the images that we feed to SeamlessGAN, architectural and loss function improvements. Also, we would like to learn to generate tileable textures instead of sampling from the model. And we would also like to explore moving beyond the idea of single image scans, which is kind of limiting. So yeah, this paper was published, as I said, in TVGG in January. You can check our website for further information and supplementary materials. You can check the Reddit post or our Twitter thread. You can check information there. We are also going to present this paper and the AI for content creator workshop at CVPR. So if you are visiting the conference, please come and say hi, because we will be there presenting the paper. So yeah, that's all from my side. Thank you for inviting me, and thank you to my colleagues at SETI for their help. Yeah.